Read first. Okay, we have this situation, a farmer, okay, previously, okay, he had planted the pumpkins and produced, and from the past experience, you know that the mean weight of the pumpkin is 5 kg, and the standard deviation is 0.5 kilogram. We don't know that whether the distribution of the pumpkin is normally distributed or not. We don't know because the question didn't say so. So now, new farming technique. And this farmer, he claims that with this new farming technique, the mean weight of the pumpkin has increased. So the variable that he is claiming is the mean weight of pumpkins. So in this case, for this one, that is the parameter for this issue. What do you want to talk about? Parameter, what do you want to measure? The parameter in this case is mean weight of pumpkins. You want to talk about the mean weight of the pumpkins, not the individual weight of the pumpkin, it's the mean weight of the pumpkin. So that is the statistic that you want to measure. Parameter means the statistic that you want to talk about. Okay, Then you have to know, you want to talk about this parameter from which population. So you have to define your population also. So what is the population in this case? Pumpkins produced by who? So every time when you read a claim or when you make a claim, you have to know your parameter and you have to know your population. You have to spell it out. Because for your 20% folio writing, correct? You're supposed to create a situation whereby you want to justify this claim. The one later. So you have to know the parameter. Parameter means what are you trying to claim? In this case, it's the mean weight of pumpkin. It's not the individual weight of pumpkin. Okay. Then from which population you draw this? You want to draw this claim. You have to state it. Now everyone understand the meaning of parameter and population? Hello? You better get this because you need to write. So no problem. Okay, good. Now, the question say that you take a sample of new pumpkin. Okay, let's, for example, okay, when you talk about sample, that means from this farm, you draw samples. So before we can talk about the sample, so do you know what is sampling? Okay, anyone have any idea what is sampling? Because if you look at part A, sampling distribution, correct? So what is sampling? Before you can talk about sampling distribution, you must know what is sampling. What is sampling? Can anyone tell me what is sampling? The result. Okay, the result. Okay, sampling is not the result. Sampling is looking at sample. So you see, this is a continuous tense. Looking at sample. After sample. One sample not enough, another sample after sample. Okay. And many, many more. But what is the condition of the same size? And from the same population. So that is called sampling. So now you have to fix the size first. So now, for example, only, for example, okay, the farm produced 1,000 pumpkin. Okay. So from this 1,000 pumpkin, I'm going to draw sample after samples. And my sample size is 30. That means each sample I draw 30 pumpkins. That means, and the sample that you draw must be a random sample. That means you take out one pumpkin. Out of this 1,000, you take out one pumpkin. You weigh it, you record it. Then after that, you put it back again. Then you take out another pumpkin, you weigh it, you record down. So that is called sampling. Hello? So how many, so sample size is 30. So how many, my question is, how many possible samples can be drawn? Can be drawn from here. Huh? If you count, it will be 1,000 C30. You count how many possible? How many possible sample? Hello? Count, please. Oh, someone has given me 2.43 times 10 to the power of 57 samples. Is it possible for us to do all? Definitely no. Okay, so when the population is too big, if we want to know about the population, we draw samples. But if you talk about 1,000 pumpkins, still possible to weigh all the 1,000 pumpkin, correct? And get the mean, correct? But it's also too many. 1,000 pumpkin is a lot. If I only produce 10 pumpkin in the farm, I can anytime just take the 10 and weigh it. Do I need to do sampling? Someone answer, please. I definitely no need to do sampling, correct? So if your population size is small, you don't have to do sampling. You can know about the population easily. But if the population is too large for you to cover all, then we need to do sampling. So now, our aim now is, can I just based on the sample, like Mr. Rick got one sample, correct? Okay. So one of the sample, okay, the one of the sample mean is 5.2 kg. So can I use one sample mean to conclude that is increased? Can or not? If I take another sample, for example, I take another sample. Okay, the sample mean is go like that. I get 4.9. So can I just use? So number one, samples tell you that, oh, Mr. Rick claim is justified. Number two, no. So each sample, the sample mean will vary, correct? So this one, what we call is sampling variation. It will vary. So what we need to do is, we want to know how is this sampling distribution look like. We know each sample, if you get the mean, each of them will vary from one another. Okay? So far, anything? So you cannot use just based on one sample value, sample statistic to justify a claim. This sample doesn't justify. Next sample justify the claim. So which one am I going to take? Yeah. So that's why statistics, they want us to study the sample distribution look like. How is the sample distribution look like? So that's why I say, does Rick sample prove that the new mean weight of his pumpkin is exactly 5.2? So what is the first answer? Can someone answer that? Hello? Student? When I'm discussing statistics, you better give me the answer. If you don't, you see the result that you have in your S85. So what is the answer for A? What is the answer for A? And give me the reason. You all don't want to give me the answer, is it? Then I just keep quiet. Can someone answer A? Someone have answer as, someone has answer as no, as sampling variation is present. Okay, I think no because of sampling variation. Okay. So that can be the answer, no, because the mean of this sample cannot represent the mean of the population. Can or not? Due to the sampling variation. Okay, now, in what range of value is likely that the new mean weight of pumpkin lie? So this one you definitely cannot answer. Okay, because I haven't teach you what you're supposed to know. Does it matter whether Rick choose a test a smaller sample or a larger sample of pumpkin? Definitely it does matter, correct? If you choose a larger sample size, okay, larger sample, that means it give a better representation of the population, am I right? So the sampling variation should be smaller, am I right? So how can we establish the likelihood of whether Rick claim is correct or not? Okay, so all these other two questions, we will do it afterward. Okay, so now you know. So from now onward, we are going to talk about the sampling distribution. Okay, we are going to, in this chapter, we are going to talk about 3 sampling distribution. One is the sum. The one I will talk about later. The other one is the sample mean. Then another one is the sample proportion. Okay. Yeah. And I'm going to introduce to you a powerful theorem that is stated in page 261. that enable us to know the distribution of sampling distribution. Okay, now, so I'm going to explain this using this example. So we talk about the pumpkin produced by this farm. So this is our population. X is the weight of a pumpkin. Okay. So this population, we know that the mean is equal to 5.5 kg and the standard deviation equal to 0.5 kg. Yeah. So you see, I put here. So I say the value. Okay. The distribution of this population may not be normally distributed. Okay, maybe you have a distribution like that. So these are distribution, what do we call it? Aha. Hello. Negatively skewed. You all forgot about all this, or left, or skewed left. Left skewed. Right? So from this population, sorry, let me, this is not a topic that is easy to explain. Okay, from this population, I'm going to draw lots of samples. Samples, samples of size 30. Okay, so each sample, the distribution for sample 1, each sample, the distribution may be skewed as well. Okay, I put a, okay, maybe skewed like that. So from each sample, I find the sample mean. Okay, sample mean, how is a symbol like? X bar. And 30 is to tell you the sample size. So I got 1 sample, I got 2 sample, got 3, I got many, many more. Okay, each one maybe is skewed left as well. Okay, so this is the distribution of individual sample. So this is the distribution of each individual sample. So I got many of them. So each of them, I find their sample mean. Then I want to talk about my sample mean distribution. Okay. So according to CLT, what is CLT? Central limit theorem. CLT, the moment I write CLT, according to the central limit theorem, if the sample size is greater than 30, by terms of rule, our book, some they use 10. So the sample mean distribution. So my variable is what? So each of them, I find their sample mean and I plot the graph. Okay. So it will tell us the shape of the sample mean distribution. It will be normally distributed. So your variable is sample mean. You are studying the sample mean, not the, is it the individual weight of the pumpkin? We are studying the mean weight of 30 pumpkins. Are you clear? We are studying the mean weight of 30 pumpkin, not the individual pumpkin. Not the weight of individual pumpkin, okay? So, according to CLT, if the sample size is large enough, that is 30, then the mean weight of 30 pumpkins will be normally distributed. So that means the sampling distribution for the mean weight of 30 pumpkin will be normally distributed. Okay, so that is the first part. Second part is, it is telling you that the mean of the sample mean. So this is our sample mean. So in another word, I can say this is our sample mean population. So the mean of the sample mean, how you write it? The mean of the sample mean, that is your variable, is equal to the population mean. This is the population mean. Okay. Third. Okay, what do you think all this mean will be? Will their variation be big or small compared to the variation of the weight of individual pumpkin? Class? The mean weight of 30 pumpkin, their variation, will it be bigger or smaller than the weight of individual pumpkin? Can someone answer me? Bigger? Why you say bigger? Let me, I'm talking about standard deviation of this. You say it's bigger than the standard deviation of the population. I mean, it's bigger than the variation of individual pumpkin. Do you think this is correct? You go by logic. Yes. Individuals should have wider. When you take an average, you lump up already. So each one, the variation should be quite close. Shouldn't be vary that much compared to individual. So it should be this way, right? Am I right? Okay, because each sample is a representation of the population. So their mean should be quite a good representation of the population mean. Am I right? The variation of the mean should be smaller. Okay, so according to CLT, the standard deviation of sample mean distribution, okay, is equal to the standard deviation of the population divided by square root of n. So standard deviation of the sample mean Are you okay? So that is cause the one. So central limit theorem is a very powerful theorem to let us know how is the shape of the sample distribution look like. And the relationship between the population mean and the sampling distribution mean. Are you okay? So it's a theorem. So if you really want to do it, then we have to take a long time. I cannot take such a big sample and let you do it. Okay? So through this discussion, I'm just, yes? Okay. Through this discussion, I just want to point out to you. Okay, I just want to point out to you, first of all, whenever you see a claim, you must state the parameter, you must state the population. And what is sampling? Why must we do sampling? Okay, can anyone answer me why we need to have sampling? First of all, what is sampling? Look at sample after sample after sample after sample of many infinite sample of the same size and from the same population. Then from each sample, we calculate the parameter that we want to talk about. Then we do the distribution of sampling. Then we use central limit theorem to help us to solve the problem. Okay, now my another question is why we need to do sampling? Why sampling is important? Why is sampling important?
Because some populations are too large.
Huh? Yes, because the population is too large, correct? It's impossible for us to get the data of all in the population. That's why we need to do sampling. And sampling must be random. So this is important. Central limit theorem here is important. Thumb of rule. Like sampling, like for example, I want to know the mean weight of Malaysians who are 17 years old. You know, can I cover everyone? Impossible. So I have to take sampling. So when my sampling, I must be random. So I cannot pick from all from town. I cannot pick all from kampong, from rural area. So I have to randomly pick. So how to randomly pick? That is when you learn more about statistics, then you will get to know. Okay? Hello? Okay, so sampling distribution, we have three types. One is sum, that is in chapter 9, part A. The other one is mean, that is in part B. Then the other one is in part E, sample proportion. So that one I will one by one teach you. So what is the shape of the sampling distribution? It will be normally distributed. Yeah. Hello. Can I not? Mean means the average. Okay. So any question? Remember, central limit theorem is a powerful theorem that enables us to know the shape of sampling distribution. Yeah. So now can we go to, okay, now we go to exam type of question. Okay, exam type of question. After you know what is sampling, after you know, okay, we cannot justify a claim just based on the result of one sample. Okay, the one I will teach you when we come to confidence interval, okay? Okay, so now can we go to example 1 in page 255. Example 1, huh? So this is considered as my population. Okay, when you see example in the book, correct, they are not practical. Huh? Okay, I just want to tell you what do I mean they are not practical. It's just giving you something so that you can have a visual of it. Okay, this is my population. Okay, now, and they put there S2 is equal to X1 plus X2. Okay, now I want to explain to you this one. Without me explaining, do you think you can? So this is my sample. Okay, what is the sample size? Okay, am I finding the sample mean? Am I finding the sample mean? No, I'm finding sum of the sample. Are you clear? If I put an S in front means sum of the sample. In another word, the total. You'll see more of this word than the sum, total of the sample. So now, and the sample that you draw must be a random sample. What does that mean? So this is my population. I have this number 2 and number 3. So now I draw the first one. If I draw 2, then I have to put these 2 back again before I draw my X2. Understand? So that means your X2 can be 2 also. This is called random sample. Random sample means to be selected as part of the sample. In another word, must be with replacement. Understand? Must be with replacement. So that means you have one sample, 2, 2. So sum of 2 will be 2 plus 2, which is 4. Probability of getting both 2 is 2/3 times 2/3. That is 4/9. Another sample I can get is, the first one is 2, the second one is 3. So sum of all these sample will be 2 plus 3, which is 5. And the probability will be 2, 3 will be 2/9. Or I can also have 3, 2, which is 5. Is also 2/9. The fourth one, 3 and 3. So sum of these two will be 3 plus 3, that is 6. 1 out of 9. So these are the outcome. So you build a table. It can be 4, it can be 5, it can be 6. The probability will be 4 out of 9. 5, you have 2 here, 4 out of 9, and 1 out of 9. You understand? And if you want to find the mean, okay, can you find the mean for the population? And the standard deviation for the population using your GC? And can you find the mean for the sum of the two? And the standard deviation for sum of the two? Can you tell me? Hello? Class? Forgot your one bar stack. Go to stack, edit.
Miss,
Huh?
Miss, for population, I got the mean 2.333.
2.3.
Yeah. And
Standard deviation?
0.471.
0.471.
Yeah.
How about this one?
Still inputting.
I can give you the answer because I know the formula already. 2.3 times 2. 4.6. If I'm wrong, let me know. Am I right? Yep. Okay. So that means it's trying to tell you that there is a formula link between the two. Okay. So there's a formula link between the two. So I'm going to give you the formula. And you have to memorize the formula. So that means, okay. Okay, if my sample size is n, so the mean of the sum of the sample size n is equal to n times the mean of the population. And the standard deviation of the sum of all the n, all the element in the sample will be equal to the standard deviation of the population times by square root of n. So this is the formula that you have to remember. Write down in your notes. Are you clear? So out of these two in the population, I also can draw 3 to find the sum. Yeah, it doesn't mean that I only draw 1, 2. I can draw 3 as well. Okay, that is the investigation what to do. Okay. You want to do this for draw 3? Let's see what do I mean by draw 3, huh? Cannot? So this formula is important. So I'm going to show you what do I mean by draw 3, sample of size 3 from here. Huh? Can I? Okay. So just now we have this. Okay, I write down this. This is my population. Huh? 2 and 3 population. Probability is 2/3 and 1/3. Huh? So I want to talk about S3. So I can have 2, 2, 2. So this one, S3 will be 6, right? Hello? So probability of getting 6 will be here. 2/3 to the power of 3. So that is 8/27. Okay, so I can also have 2, 2, 3, or 2, 3, 2, or 3, 2, 2. This is something like a binomial. Okay, so you can use your binomial. So this one, all this, the S3 will be 4 plus 3, 7. So probability of getting 7, yeah, will be equal to 3 times of 2/3 to the power of 2 times 1/3. Yeah, so 12/27, right? So you can also have 2, 3, 3. Okay, this one also got 3 forms. So this one, the sum of 3 will be equal to 8. So probability of getting an 8 will be 3 times of 2/3 times 1/3 to the power of 2. So you have 6/27. Then the last one is all is 3. Okay, so S3 will be equal to 9. So probability of 9, 1/3 to the power of 3. So it's 1/27. So you see, you add up 8, 12, 6, and 1. Yeah, 27. So you have to, you also can build like that. So this is the one about the sum. So that is exercise 9A. So afterward, next lesson, I'm going to talk to you about the distribution of the sample mean. Yep. Okay. Can or not? Then the central limit theorem. I will do a few questions. Okay. So I'll see you at 4 o'clock. Yep.
Okay.
Okay. Thank you, class.
Thank you, Miss.
Thank you, Miss.
Thank you, Miss.